Hello and welcome. Welcome back. If this is your, more than first time being here. Today we have course schedule two, and I've previously done the first part, which is course schedule one. I guess. Very interesting question. Um, and without further ado, let me just get into the problem description, right? So we have, there are a total of NAM courses. You have to take labeled zero to NAM minus one. You are given an array prerequisites where prerequisites I equals AI, BI indicates that you must take course BI first to take AI, right? So BI is the prerequisite of AI. Basically, that's what it's saying, right? So BI points to AI. You can also think about it that way. So, for example, the pair 01 indicates that you have to take course zero, you have to take the first course one, right? So take care of course one before you get to course zero, right? The second element is pointing to the first element. You can think of it that way. So return the ordering of courses you should take to finish all courses. There are many valid answers. Return any of them. If it is impossible to finish all courses, return an empty array. Now, this question is very similar to course schedule one, in that the scenarios in which you can't, um, you know, uh, finish the courses are when you have cycles, right? And what is a cycle basically, right? So basically, we can think of this question in terms of graph and graph nodes. And in fact, I think it will be very helpful if I go on a drawing board instead. So, right. So basically, you can think of their prerequisites, right, in terms of a graph where the element being pointed to, right, is your destination, and then the element that points to another one is the source, right? So in this form, we have AI and BI basically, right, as your tuple, where you have what? Note that each of them are like node values, right? So BI is going to point to AI. And if you construct a graph, you'll be able to see um, all the nodes pointing to each other. Now, the scenario in which you can't finish all your courses is when each course depends on another course, right? So we do have a cycle in it. And if there is a cycle, right, you can't, because you can't complete the courses because every course is a prerequisite of other courses, at least in that cycle. So you are never able to know where to start or where to finish, basically, and you can't start or finish, right? But once you can't start because it's depending on other courses, and you can only take one course at a time, and so on and so forth. So how are we going to approach this question? Well, as I did in the previous question, and I'll do it again here, right? We're going to use algorithm, like topological sorting, basically, to solve it. So how are we going to use topological sorting? Well, basically, so topological sorting is going to be that for every element that's being pointed to, right, will have a value called an in degree. So say BI is pointing to AI will have an in degree of one, BI will have an in degree, depending on if no one is pointing to BI of zero, right? So if no one is pointing to BI has an in degree of zero. And then we pre-process the elements who depend on no one, right? Those are the classes we can take first. The classes with no prerequisites, essentially, right? And then after taking those classes, then we'll probably have fulfilled at least one more prerequisite. So then we can take the other classes now that depended on the ones that had no prerequisites, right? So if we take those ones out and we reduce the in degrees, sequentially, right? What happens is that eventually, if we are able to take all the courses, every element at one point will have an in degree of zero, meaning it has no previous dependency. So let me just use the graph, right? We have here four courses. Look at the prerequisites and notice that BI points towards AI, right? So for the first, I have 0 and 1, right? So course zero is going to point towards course one. So course one depends on zero, right? And then for the next one we have 2 and 0, right? So basically, again, zero is pointing to two, right? And from here we have 3 and 1. Again, one is pointing towards three, and then we have 2 and 3, right? So I believe two is also pointing to three. So the graph looks messy, but this is um, one way of representing the graph, I guess. Okay, cool. Now we are going to look at the in degrees of every element. Right? So initially, zero has what 0 in degrees here. One has one element pointing to it, so it has an in degree of one. Three has two different elements pointing to it, so it's two. And two has one in degree, right? Just one element here. So we first process what the one with no in degree, so it's zero. We take zero out. This is the one with no prerequisites, so we can take zero and cause zero. Right? So we take cause zero, put it in our list, and then we reduce the number of in degrees or dependencies, sequentially, right? So zero, one dependent on zero, right? So one minus is in degrees on zero, right? So there's no pointing to zero. A zero is not pointing to it anymore, so zero here. Same with this chain, right? You have what zero here. Cool, cool. Now we have two elements with what in degrees of zero, so you can process any of them first. So let's say I put in one, right? Then this goes down, and then this becomes one, right? In degrees of one, and then later on I put in two again, right? In degree of zero, and um, two is in my list now, and this in degree of one now becomes what zero, and you see we can take the courses in this fashion, right? Like 0, 1, 2, 3, right? Which is also one of the correct orderings, right? Another correct ordering is here. If you chose this in degree first, you decide to process this one zero before the rest. So these are correct orderings, right? So when we are not able to do it, it will be when let's say we have a cycle like this, right? So let me have nodes two. Sorry, my drawing is not that good, right? So we have these three nodes, for example, connected, and then it's like this, and then it's like this, and it's like this, right? You see in this case, three depends on what's two depends on one depends on three, and so on and so forth, right? So the in degrees of, let's say what are the in degrees of three, right? It's one. In degrees of two is also what one. In degrees of one is one. So we don't have, for example, in this graph, any element with a zero in degree that we can process first. So then we'll have to return what an empty array whenever we detect a cycle. And we can detect cycles basically by the number of elements we process using our Khan's topological sorting. So because we're able to process any elements here, right? It's wrong. But here we're able to process all four elements, which is what essentially we want to do in the first problem, right? Okay, so without further ado, let's just get into the coding, guys. Right. So the first thing that we want to do is to create an adjacency list, right? So that we can um, benefit from that. So that is a list of integers, right? It's a new array list for size n, right? So for every element in our adjacency list, essentially, right, we'll put in an empty array list, right, and then we'll add later on we'll add the subsequent nodes not necessary, right? So for pre, let me just call it prereq. You know what prerequisites? Um, U is the first element, right? The element that's going to be pointed to. So it was prereq 0. And V will be prereq 1, right? And before that, also, I wanted to keep an array to keep the in degrees essentially, right? So in degrees, 10, and then it's going to be size now courses basically, right? And in fact, this should be num courses, not n. The same here, right? So what we do is that the element that's being pointed to is our zero, right? So for zero, I'll increase this in degrees by one, right? Hey, so the element being pointed to is u, right? So I increase the in degrees of u by one, and then I just add to my adjacency list, right? So I add for v that it has a neighbor what's u, right? Because v is pointing to a certain element, so that is its neighbor, essentially. From then on, we just do count, topological sorting, where we first add the element with, zero, um, sorry, the elements with zero, what do you call it? Zero dependencies, right? So an in degree of zero. Also, we want to keep our results, right? For every element that we process, we add to our results. So, it's a new array list. And now, basically, I'm going to go through our in degree list, right? So, for k is equal to 0 and k is less than in degrees of length. Now, if the in degrees of k is 0, right, then we add to q, to q dot add k, and also every element with an in degree of 0, I'll add to our result, basically, right? So that is done here. And now we want to process it doing count topological sorting, basically, right, which is the elements with so basically, I'm going to go through the queue, right? And the integer that we pull first is going to be q dot pull, and I want to call that current. And then after working with current, right, I want to, reduce its in degrees, the in degrees of its neighbors. I've already processed current, and then what I want to do then is to, add. Um, and then I want to do, reduce the degrees for its name. Actually, I was just thinking about it that like we do not want to add to the result here. What I want to do is that once I process an element in our queue, then I add to um, our results basically. And so here I'll be like result dot add current, right? Add current, and then for its neighbors, then I'll work on them, right? So I'll say for int neighbor, what the adjacency list of current when I explore for the neighbor. So in degrees of the neighbor, gonna reduce it by 1, right? And then I'm going to check if the in degrees of the neighbor is now equal to 0. If it is, then it's valid for processing. So I'll say q dot add what's neighbor. Else I won't do anything, just continue. Right. So one thing we want to do is now check, right? If like once our while loop is turned into, we don't just return. We want to check if we process every element. Right? And how do we check if we process it? Well, basically, if our result has every element, basically, right? So if result dot size, if that is not equal to num courses, right, then we know that we have a cycle, right? So cycle. So what we want to do is return what's an empty array, right? This is what new array list, an empty one. Else, what we want to do is just return our result, right? Cool. That makes sense to me. Don't have a compilation error here, but array list cannot be. Oh, it's an int list. Oh no way. Oh, I shall check it. Actually, we have result is an int list. Okay. So if it is an int list, then let me change its signature here. Because I'm sure people who are using Python already have an issue with it. Okay, so our result should be an int list instead of size num courses, right? And then basically let me take this out. And then we add to our result. Instead, I want to keep an index as we add, basically, right? Index plus, sorry, int index. And then our index will show us the position of results to add our current element, right? So index is equal to current. Actually, let me hit plus plus, right? So the index increases as time goes on. So then I will check if what our index, if our index is at the end of If our index is equal to now, of course, right, then we process a single element. But if it's not, then we return a new empty list, right? Empty one, no elements. Or if it's not, then we return what our result. And so we pass for the first three test cases. And then basically we beat 91% of other Java users. This just counts topological sorts. Now, previously than the first question, um, what's the runtime, right? Well, O of n operation here. Again, O of n operation here, and same thing, O of n operation in our while loop. So in the worst case scenario, it's going to be O of n. I hope you guys O of n, time complexity, right? The space complexity is also going to be O of n. We have a linked list or a queue, and I think that's it. I hope you guys got the most from this video. And if anything, please do like and subscribe, and I'll see you guys on the next one. Peace.